PPT. This one, yeah? PPT, down. So good afternoon to all. So I am Tripathi, anyway. Professor Abhishek has already introduced me to all the participants. So it is my presentation or my webinar is on light combat helicopter LCH overview. I will take you back to 10 to 12 years back. What happened? How we started the project, and what are the difficulties we have faced? How we have overcome these difficulties. And then now we are presently we have already implemented or inducted the helicopter into the forces.
Sir, I'll request you to make the slides full screen. Okay. Right now it is still in the.
It's close.
By pressing the F5 button, maybe. Okay.
Yeah. Is it okay, sir?
Probably it is still coming, not yet full screen.
Sir, you could able to see the screen,
it is still in the normal view. Okay. It is not in the full screen view yet. Okay. So maybe you have to place the slide so and then make it full screen.
Give me a few seconds, please.
Sure. Please, no problem, sir.
First question, don't put normal view.
F5 button normally makes it full screen. F5.
Oh no. Okay. Still is not here. No. Sir, now is it okay, sir? Now?
No, it is still in the same view actually as earlier. So maybe I think the reason could be I would say stop sharing and maybe share the full screen actually. Maybe you have chosen an application, so that may be the problem. So you can stop sharing, okay, and then share when the option is there. You select the full screen.
Please give me a moment.
Please, sir. Please go ahead. Yeah, take your time.
No?
Yeah, please continue, sir. Now it is working fine. You are muted, sir. You have to unmute. I think you are still muted. Actually, I cannot hear you. Screening is coming out fine. Please unmute yourself. Yes. Yeah. The audio is back. So please start. Sir.
So you could able to see the video, sir?
Yes, sir. Now it is fine, sir. Please continue.
Yeah. So sorry for the interruption in the beginning due to some computer issues. Okay. Once again, good afternoon to all the participants. So I will be explaining to the participant how this LCH came into picture. I will take you way back to maybe 2009 or 10. So now I will give brief introduction about LCH. So in the beginning, there is a need for an effective weapon platform to deliver precision strikes at high altitude was projected by armed forces. So armed forces indicated that India should develop a weapon platform to deliver precision strikes. So from there only the concept has been started. So the concept of LCH has been initiated from that day onwards. Now, for briefly speaking, light combat helicopter is a dedicated attack indigenously designed and developed by HAL to meet the operational requirements of defense forces in combat role. Because earlier in India, there was no combat helicopters of our indigenous design. And LCH incorporates advanced technologies and stealth features for effective combat roles and designed to carry out roles such as destruction of enemy air defense, counter-insurgency, anti-tank, counter-surface force operations, etc. The LCH is a 5.8-ton all-of-weight class helicopter powered by 2 Shakti engines. The helicopter is equipped with mission sensors for target sighting and weapon systems such as 20 mm turret gun, 70 mm rockets, and dual-tier missiles to provide lethal capability. LCH has been qualified under stringent operating conditions at sea level, hot weather, in desert region, cold weather, and high altitudes and Siachen range. At the end, the helicopter demonstrated its weapon firing capability also during various defense exercises. And the LCH is designed for Indian Army, Air Force, and has been certified for military role by Center for Military Airworthiness and Certification, CEMILAC, the Indian Military Certification Agency. Recently, the LCH has been named as present by our Honorable Defense Minister. Now, I will show you the performance parameters of LCH. If you look at the performance parameter, if you search Google or if you look at the LCH performance parameters on the public domain, you will see that LCH has a service ceiling of 6.5 kilometer. It has a ferry range at sea level with full internal fuel of 580 kilometers, hover ceiling up to 5 kilometers, then maximum weapon load it can carry around 1000 kg. It has an endurance of 3.5 hours, maximum takeoff weight of 5.8 tons, and it is installed with 2 RD and 1 H1 engine of engine rating of 1032 kilowatts. It can fly at a max speed. They call that the dive speed of 337 kmph, and it has a max cruise speed of 270 kmph, and it can hover up to an altitude of 5000 meters. At the last, it has a G limit, load factor they call. It is at a plus 3G and then a negative G of 0.5. Once again, the endurance of 3.45 hours, 3.45 to 5 hours. Then how these parameters came? When somebody thinks this one, okay, these parameters now it is live, everybody could able to see this one that the parameters are there for LCH. Then how we derived, how we obtained these numbers. Before proceeding to that stories, I will just give a brief introduction on the LCH advanced technology features. If you look at the picture of LCH, it has an integrated dynamic system. It has a hingeless main rotor, bearingless tail rotor. It is powered with Shakti engine, as I have told you a few minutes back. It has a crash-worthy crew seat and there a glass cockpit. In addition, it has an anti-resonance vibration isolation system. We call it as ARIS. It is there on advanced light helicopter also. The same has been implemented on LCH. Then what are the survivability features of LCH? LCH is integrated with a nuclear detector. That means it can detect the nuclear weapons. It has a narrow fuselage and flat glass panel to reduce glint. Then bulletproof windshield to keep away from the attack. Then it has armor protection. Generally for all attack helicopters, all the combat helicopters, they have a armor protection. Then crash-worthy bottom structure is there for the any emergency landing or any hard landing. Then crash-worthy fixed tricycle wheel landing gear is there. It has a canted flat panels for low radar cross section, RCS it called. It has dual channel FADEC, dual electric power, dual wave pump, twin engine, dual hydraulics, dual FCS. Now, I will take you back to 2009. So how it happened? Today we are single LCH is flying, it is getting inducted into Indian Army, Indian Air Force. Then how the story started? It started almost in 2006. When the 2003, the requirement has been given to HAL that HAL should develop, or India should develop one light combat helicopter, or it's called light attack helicopter. In that way, it has to develop for Indian Defence Forces. Then the task has been assigned to HAL to go ahead. So initially, from the drawing board, we have started designing the helicopter. We have done faster. If you look at the picture, it is like a wind tunnel testing. We have carried out the LCH wind tunnel testing in our wind tunnel. Then somebody may ask, what for you are doing all this test? I want to check that whatever design I have done over the surface of the helicopter, or the surface of the model, what are the forces are being developed and what are the moments it is getting created and what are the pressure values. This can give me an insight that whether whatever I have designed, whether it can comply those missions or not. So from the wind tunnel setup, if you see there, we have done dedicated testing. Almost the test comprises of testing the helicopter at different angle of attacks, different azimuths. That means you can take that we at different azimuths in the alpha and beta directions. Then we have done the hover testing, then accumulated all the data over the entire range of the surface with respect to force and with respect to moment and with respect to the pressure coefficients. Because force and moments, these are all aerodynamic coefficients, which give me some idea this one that what is the lift can be generated by the every control surfaces, and moments also will give me an idea this one that what will happen to the handling quality of the helicopter, and the pressure coefficient whatever I have measured, this will give me an idea this one that what are the loads are going to be absorbed by the components when it is in the flying zone. If you look at the two pictures, when I finished the wind tunnel testing, then I have built up one full scale mock-up. Full scale, it is just like a replica of the helicopter to check that really how the helicopter look alike. It is not paired with an engine or anything. It is just only with it is like a basic structure. Just to check this one that with whatever I have designed, the height of the helicopter, the blade, and if you take the main rotor and tail rotor and the landing gear, how it look alike. Suppose a pilot can, it is easier for the pilot to ingress or egress or not. So those things, and how a pilot will visualize the cockpit. So for that purpose, we will develop on full scale mock-up. Then subsequently, based on the feedback from the pilots and from the certification agencies, we try to modify it. Then you can see that it has been converted to a one more mock-up, which is having all the features, which will be just like a replica of the actual helicopter. You can see from in the beginning, we don't have an EO pod. If you see that a dome-shaped structure is there, which indicates that that is a electro-optic pod is there, and all glass panels, you can see it. It just look like a helicopter. Now I will take you to the capability of LCH. As I have told you in the earlier slide, LCH had the capability for carrying external stores in 4 stations. There are 4 stations, one on the LH side, 2 are on the LH side, and 2 are on the RH side. Each one is capable of carrying almost 250 to 200 kg loads. Then carry out, it is having a capability to carry out operation from sea level up to the service ceiling, that is 6,500 meters. It has a forward airfield operation. It can fly up to 270 kmph at sea level in external store configuration. That means I can integrate some external stores like a missile or rocket. I can integrate, and the helicopter will be able to fly at 270 kmph. Then forward flight also it can do it. Suppose an engine failure is there, helicopter can continue flying in forward flight in case of engine failure up to 4,000 meters. These are very, very stringent requirements for a helicopter. Then in case of adverse wind conditions, like you know, in India, so many places are there where the wind conditions are very, very stringent. You may get wind speed in different directions. That will be crosswind will be there. So we have to test the helicopter and we have to comply that whether the helicopter can take off or land in adverse wind conditions up to 30 knots or not. So these are the capability of this helicopter. This slide gives one insight this one that when we started the testing, once the mock-up is ready, then the helicopter has been built with all the accessories like main rotor, tail rotor, engine, then on the cockpit, whatever is there. Then the first flight happened on 29th March 2010. Subsequently, we have manufactured one more prototype that is called a technology demonstrator 2. It has made in its first flight on 28 June 2011. Then we have done one more prototype that is called the technology demonstrator 3. That has come 12th November 2014. Then the fourth technology demonstrator that has flown for the first time on 1st December 2015. Why this 4 prototypes? Somebody may ask, you would have done the testing on the first prototype. So when I flown the first prototype, at least I'll come to know really this, what are the missions has been asked by the customer. It can comply the missions or not. What are the difficulties are there? What are the observations are there? Whether the helicopter is flyable at all these stringent conditions or not. So from that, I will get some idea or get some insight this one, that is there any requirement to modify or any component, or is there any requirement to modify any external configurations of the helicopter so that it can comply the missions. Then only the technology demonstrator 2 comes. Then technology demonstrator 3 comes, this one, that further what are the improvements are required by the whatever has been raised by the customer, further what are the improvements are required. Then it comes to the TD4, technology demonstrator 4, it is just a replica. It is like a replica of the production helicopter. How it looks a production helicopter, it's like a production SOP. They call it standard of preparation. It is a production SOP helicopter. Now, so once again, I am taking back why these 4 prototypes are there. If you look at the left side of the screen, you can see this one. This is called the first prototype of the helicopter. You may ask me this one, that what is the changes you have done? So this picture, what you are seeing, that is called the prototype 1. So which has done its flight in 2010, and it has given us some different observations, this one, that with respect to performance. Then our study started how to gain enhanced performance in the helicopter. So that has given us a modified helicopter, which is on the right side of the screen. You can see that is a helicopter there, which is the helicopter with enhanced performance. Then what I have done? So when I want to enhance the performance, there are 3 to 4 things I have to incorporate without touching the internal of the engine, integrated system. That means the systems which are there already integrated inside the helicopter, I cannot touch it. If you speak on aerodynamics, if I have to do certain aerodynamics improvement, I have to do only on the external configurations. Because nobody will allow me already all the electrical sensors or avionics sensors or the transmission system, engine system, everything has been integrated. So only somebody will allow me this one, that you can do some modifications externally to get a better aerodynamic performance. So I started studying. If you see look at the first point, it is called the aerodynamic armament wing. Earlier I had a box type armament wing, so I have changed it to the aerodynamic armament wing. Our group, we have done a dedicated study that which aerofoil will fit to the helicopter. Then how the armament wing, which is going to carry the weapons, it can sustain that load. In addition that, it can give a major lift. It can upload the tail rotor. In that regard, dedicated study has been carried out. Both mathematical computation we have done. In addition to that, CFD studies also we have done. Then we have derived the armament wing of shape. We have almost some 5 to 6 months of study has been carried out to derive this armament wing. Then it has been integrated with the helicopter. Go back. Subsequently, then our team HL, we started searching this one. We started seeing this one, that really what are the other modifications can be done on the helicopter to improvise the performance. Somebody asked me why improvise the performance means. It is indirectly indicates this one, that improving the aerodynamics of the helicopter. That means reduce the drag. Helicopter can fly at a little bit faster speed. So we have done, my team, we have done a dedicated study and then look into the full each beat corner of the helicopter, and externally what are changes can be done. Then we have 2 landing gears. Generally, landing gear drags are very high compared to the total. If you see the total fuselage drag, landing gear consists of 1/3 of the total drag of the helicopter. So we have done some landing gear fairings we have implemented on the helicopter. Subsequently, we have a tail landing and fairing which is at the rear end. There also we have implemented some fairing. We have done dedicated studies with the CFD and then theoretical studies also. Then implemented the tail landing gear fairing and the main landing gear fairing. Then on the scoop, which have been kept for inlet and outlet, that means for cooling and cooling of the components, whatever they are inside the engine compartment or inside the gearbox area, to heat that whatever scoops have been provided. We started studying this one, how the scoops can be modified so that we can reduce the drag. Anyway, scoops are required for improved performance of the engine and transmission systems. What we have done, very good modification over the top cowling so that the drag area can be reduced and we can get a better performance. Go to next. Then you can see that there is a pitot probe location is there. Initially, we have put the pitot probe to measure the airflow. That means airflow means if pitot probe generally it will give me this one, that what is the total pressure and what is the, this is just general phenomena. It will give me the total pressure. It will give me the static pressure. From that I will derive the dynamic pressure and check that really what speed helicopter is flying. So initially I have put the pitot probe there. Then when I have seen that when helicopter started moving faster, how to acquire the data properly without any error or without any tolerance or differences, then we have done certain studies with respect to CFD and theoretical computations, and then we have modified the pitot probe location so that it can capture the actual speed of the helicopter with minimum error. That we have done. If you see the right side of the screen, those modifications have been carried out, and we could able to get the accurate speed of the helicopter in every flight regimes. That is also a modification we have done. This modification when next. When we have done these two modifications, this modification given me in the technology demonstrator 2. Now, next comes this one, that I have to do a optimization of the engine air intake, because finally the air intake what is being implemented on the helicopter, when I deliver to the customer, I have to implement the infrared suppressor system on the helicopter. When you integrate the infrared system suppressor system, that is called IRSS on the helicopter, you have to provide a secondary air intake. Okay, just behind the normal intake. So towards that also we have done studies. Those two things are not there in the technical demonstrator 2. So we have done a dedicated study to how to improvise the air intake performance. Generally, finally, what will happen if you design a better air intake? It will give a very reduced installation losses, which can give me a better engine performance. So in that regard also, my team has done a dedicated study, and then we have improvised the air intake so that the engine performance can be enhanced, and helicopters should fly at with reduced losses at a faster speed at all the altitudes. So from left side of the figure, you can see that contour. From that, you can see the right side, all the modifications have been carried out, and then it has been integrated in helicopter that you have got in the technical demonstrator 2. Now comes to that. This is so now all the prototypes are available. Now what is there? How to comply the missions, whatever has been asked by the customers. That means whatever has been raised, that if your helicopter should be able to comply these missions, that means it should be able to fly at this altitude, at different altitude, different speeds. It should be able to take up certain maximum elevate. It should be able to give me a good means like a low speed handling capability. It should give me very faster acceleration. So to demonstrate all these things, I have to subject the helicopter to different types of trials. Trials means, so if you see that on the top performance too, so when I go for the trials, I will do assessment of the performance and handling quality of the helicopter. I have to measure the component load for life estimation, because finally I have to tell that when the helicopter is delivered to the customer, really what will happen to the component load, what will happen to the life of the component loads. Then third one, I have to assess the helicopter performance encompassing the entire flight envelope. As you have seen in my flash slide, I have told you that helicopter servicing has been envisaged at 6,500 meters. That means I have to do the test up to 6,500 meters and check that really this helicopter is able to capable of withstanding the speed or withstanding the component loads at different altitudes or not. In this regard, we have carried out a dedicated testing at sea level. That means that is called the sea level trials we have done. We have gone 2 times for sea level trials. Once before the improvements, once after the improvements. So when you have gone the sea level trials, generally in sea level trials, we have to look always when you go take the helicopter sea level, because sea levels in the density ratio is higher, and the engine capability and the helicopter capability also is higher, you will be able to demonstrate the maximum capability of the helicopter. The moment you land at sea level, first and foremost duty this one, that load the helicopter to add configuration and check that whether this helicopter can fly at a faster speed or not. Because those tests I cannot carry out at a Bangalore city and Bangalore, because Bangalore is at a 3,000 feet altitude. I cannot load the helicopter up to that all of it and then do the test. So I have to carry out the sea level trials and then load the helicopter from starting minimum all of it to maximum all of it and check that what are the capabilities, what are the loads and various components, and what is its handling assess, what is its handling capability. So those things have been checked during sea level trials. If you see at the lower end, one more picture I have kept it, that is called the cold weather trials. Why a cold weather is required? See, when I deliver a helicopter to the customer, as a designer, I should know this one, that whether the helicopter could able to fly in cold temperature conditions or not. That means whether the components, whatever they are in the helicopter, indirectly I can tell you that whether in cold weather conditions, the engine can start or not. If it starts, whether the helicopter behavior is different compared, because I have tested at sea level, that is a normal temperature conditions. Generally, you take an international standard atmosphere plus 15 or plus 20 conditions. When I go to cold weather, it is an ISA condition. That means density, your density value will be at cold conditions, your density value will be actually higher. So those conditions, I have to do the test and check that how is the helicopter behavior with respect to performance, with respect to handling qualities, and with respect to all the systems. That means whatever systems have integrated, is it behaving properly during cold weather? So for checking those points, we have carried out the cold weather trials. Then the last slide, you see, it is a hot weather trials. Why a helicopter had to be subjected to hot weather conditions? When the helicopter is subjected to hot weather conditions, there one point comes that why hot weather? See, it is in India, if you see the weather conditions, it varies from, at least if you go to Leh Ladakh, it varies from -25. If you go to Jodhpur, it goes to almost 40-45 degrees centigrade. So I have to test the helicopter that what its capabilities are those conditions. That picture what you are seeing, it is actually the picture taken from Jodhpur only. So we park the helicopter in the open air till the temperature sensor reads almost beyond 40 degrees centigrade, that means up to 45 degrees centigrade. Then we tell the pilot this one, that you take up and then see that the helicopter can take up or helicopter can fly at a certain speed, and was there any issues are there with respect to the systems, whether it is a avionics bay or whether the engine or the transmission, is there any observations are there. So in that regard, I have to carry out hot weather trials and comply those requirements. That means if the 4 slides what you are seeing there, it will give me an idea this one, that from cold to hot, how is the behavior of the helicopter, and at a lower altitude, if the helicopter is flying at a very faster speed, how is the behavior of the helicopter. Those details have been obtained out of all this test. Subsequently, if you see on the left side, there is a major achievement for LCH, and for the country also I can tell you, it is called the high and hot altitude trials. Hot and high altitude trials. That means you have to fly the helicopter in hot conditions and at high altitude. That means during, see, if in India, if you see, go to Leh Ladakh, you have to go in August and September and wait for the temperature to build up. Though Leh Ladakh is at an altitude of 3000 meters, 3500 meters, the temperatures in the August, September, it goes to almost 25 degrees, which is closer to some ISA plus 30 conditions with respect to international standard atmosphere. So you have to do the test and check that what is the payload capability. Finally, the customer will be utilizing the helicopter in all temperature conditions. I have demonstrated in cold weather, but I have to demonstrate even hot and high altitude also to check its capability. When you went for the trials, we have gone through all the bases and then check this one, that how is the capability. And during the process also, there is a major achievement for HL and for LCH also. We have landed at a helipad wherein no helicopter till now has been landed. That is called 4,700 meters. When I myself was there during the trials, we have monitored this one, how is the helicopter behavior, and helicopter could be able to land there with adequate fuel and payload at that altitude, and then again taken up and then get back to Leh sector. Right side, you can see that is called the rocket firing trials. Once you establish that what is the performance parameters of the helicopter, that means you have defined this one, that your helicopter is capable of flying at the required speed, at the required altitude, and the loads are well within the expected values, within the component capability, then the helicopter is built for the firing trials. Finally, aim of the project is this one, that to deliver the helicopter to the customer wherein he can utilize it as, because it is a combat helicopter, he has to use it for a rocket firing trials. So rocket firing trials have been carried out number of times, this one, that at different places in the different conditions. Then you know this on LCH, there are different types of system, external stores can be attached. One on the, you can integrate rocket pods, you can integrate air-to-air missiles, and you can integrate. And anyway, that is a gun is there. You can see the front. I have shown you that gun is there. Then in addition to that, you have to do multiple firing. That means from the same sector, you can do even rocket firing also, you can do atom firing also. So we have carried out dedicated extensive firing trials we have carried out to check that to establish the firing envelope for LCH. If you see lower one small picture is there, that is called a jettison of external stores. You can ask me why this picture. This picture why we have taken. Suppose during a trials. Now you think this one the helicopter has entered into some emergency situation. Then pilot doesn't have any option instead of jettisoning the external store. So in Bangalore, we have done a dedicated study through CFD, and in addition, we have done experimental study. That means we have done flight test to check this one that when a store is even ejected or jettisoned from the platform, whether it is having any clearance is there with respect to the helicopter structure or not. That also has been checked to 3FD and to flight testing also and evaluated, because that is a mere requirement. So this is with respect to different trials. Now capability, as I have explained to you now, in hot weather conditions, in Jodhpur, that left side picture has shown you that in hot weather conditions, LCH has the capability to take up with max allowed of 5,800 kg beyond 40 degrees centigrade. Even we have tested up to 43, 44 degrees centigrade. Then absolutely no issue. We are waiting for the temperature to come. Then it is a fast attack helicopter. On the right side of the picture, if you see that it has fast attack helicopter in India to land and take off at 4,007 meter altitude with considerable loads and loads of weapon and fuel. This has given major achievement for HL also, for country also. This one, because till now, whatever helicopter is there, whatever information we have in the public domain also, nobody can tell you this one that except LCH, any other helicopter there which can land and take off at altitudes beyond 4,500 meters with a loads of weapons and fuel. This is the achievement for LCH, and in addition, it is for HL also. These are the features. If you see, that is a dedicated combat helicopter. I have given you there the 3 helicopters are there. It is all our prototypes. It is a dedicated combat helicopter. It is a sleek fuselage with tandem seating when pilot back to back. A design for high survivability. Design with stealth features. It has, I have told you this, and the armor panels have been integrated. There is anti-armor capabilities there. And operation during day and night. So we have tested the helicopter during day and night also. Night flight have been carried out so that the helicopter is compatible for day and night. And even firing trials we have carried out even night also to check that, because as a customer you can do the firing trials during day and night. So these things also have been carried out. Then crash of the floor structure is there. Then reduced radar signature. Extensive testing has been done by at Jodhpur by DRDO lab to check that it should have a reduced radar signature for the enemy. Then reduced IR signature, because IR suppressor has been integrated on the helicopter. So from other side, you cannot see this. What are the exhaust side? You cannot locate the helicopter. In that regard also, it is like a IR suppressor has been integrated on the helicopter and it have a reduced IR signature. Then we have a directional control by push-pull cable. This is the end of the presentation. Before proceeding to other things, I will just show you one video on sir, can I continue for this?
Yes, sir, please, sir. Please. Yes.
Then we can start the question answer session or any clarification there. Yes. Yes. Sir, you could able to hear me, sir?
Yes, sir. We can hear you, sir. The video is also visible. Yes.
Yeah. This is a video showing all the LCH capability, whatever trials I have explained to you, all the trials have been captured here. This is the first helicopter. This is the TD2, technology demonstrator 2. You can see here. This is the technology demonstrator 3. Whatever. This is what I have explained to you that during Jodhpur trials, in the hot zone conditions, we have tested it in the month of June, July. This is just checking. This is the hot and high altitude trials at Leh. These are 3 helicopters are flying together for formation flight. This is a iron fist for the rocket firing trials. At you can see here the presence of our Honorable Prime Minister. This is the rocket firing trials we have carried out. From both the stations, from LS side, RS side. This is a butt firing. Before proceeding for gun firing trials, we have to check on the ground and check that whether butt firing. Then is a turret gun firing trials we have carried out at Kalaikunda in West Bengal. This is just to check this one, that what is the location, then carry out the firing. Is the air-to-air missile firing. It has been carried out at ITR Chandipur, DRDO lab. This is the initial operation clearance has been obtained by HAL for both Army and Air Force. Go to the screen, go to the screen. Normal screen. Yes, sir, I think I have finished the presentation.
Yeah, that was a really, I mean, amazing and very nice presentation. I mean, really enriching to see the journey of light combat helicopters. Okay, so we have now good time to have some discussion and questions answered from all the audience. I also have a few questions, but I'll let first the audience ask. So you can type your questions in the chat box, or you can also, I mean, unmute and ask the question yourself. Okay, so first is, I think the Vishnu has sent some message. So Vishnu, I mean, if you are there, you can unmute and ask your question.
Good afternoon, sir. Am I audible?
Yeah,
Yes, you're audible. Yeah, please go ahead.
Tripathi sir, very pleasure to see this webinar, and I would start by congratulating with all the development and possible deployment news that we are hearing.
Thank you.
And my question is, in all the photos and videos, I have seen the exhaust of the helicopter pointed into the main rotor. So is it a way for IR suppression? If yes, like, has it created any problem in aerodynamics?
Yeah. Now you asked a good question. See, during testing, actually we have done if you ask me, we have done dedicated testing, and on the main rotor blade, your question is genuine. You on the main, we know that we had also same doubt in the initial phase. On the main rotor blade, we have provided some sensors to check that really what flow it is impinging on the blade, and we have instrumented the blade to measure the loads. See, earlier, before implementing the IR suppressor, we have measured the loads. Now, when we integrate the IR suppressor, once again, for the same flight conditions, I have measured the loads, and I have checked also, we have checked that on the blade, if the IR suppressor ejection, the hot gases impinges, really is there, what is the temperature impact, and with what force it is impacting. So those checks have been carried out, and we had no abnormalities, no differences with respect to loads and with respect to the hot zone also.
Yes, sir, that was my question. Thank you very much, sir.
Okay, welcome.
So there is a question by Kushal
Yes, sir.
regarding how does the rotor design fundamentally change for very high altitude hovering, like 7-8 kilometers. I mean, right now, I think we have already for 6 kilometers or thereabout.
Yeah.
So the question is, I mean, for high altitude, I mean, how does the rotor design fundamentally change compared to that for normal sea level or low altitude or moderate altitude operation?
Now, it is a very basic thing. It is from the textbook only. Anyway, I will share with you because it's our day-to-day activities. See, when you design a rotor, the first thing comes this one, that what for with respect to hover, first thing comes the induced velocity. Induced velocity, if you see the VI, it is equal to T by square root of T by 2 rho A. T is the thrust, what you are going to, and what your helicopter is going to withstand. Suppose I will take 7 kilometers or 8 kilometers or 6.5 kilometers. So what is my requirement? Suppose a customer tells this one that I have to lift 4,500 kg or 5,000 kg at 7 kilometers. Then what will I do? That at that altitude, first I have to find out that what is the induced velocity. That means Vi is equal to T by 2. So T is equal to the whatever the alloped of the helicopter multiplied by 9.81, that is the acceleration due to gravity G, divided by 2 into rho. Rho is your air density, whatever density at that particular altitude. A is your blade area. That means pi r square I have to use it. So if your helicopter has been designed for that sort of induced velocity, then you can clearly tell whether the helicopter is capable of flying at that zone or not, capable of taking off at that zone or not. Then one more point comes. If suppose today any user asked me this one, that I want to use this helicopter, I want to take off at 7 kilometer altitude. Point comes this one, that okay, what type of engine you are going to implement in helicopter? Everything derived from the engine. So first I must know this one, that what is the capability of the engine at 7 kilometer altitude? Because first I have decided this one, that 7 kilometer altitude. If I know that this is the power developed, delivered by the engine at that altitude, then I can find out this one, that generally what will happen. The induced power, what we calculate from the textbook, it is generally around 70 to 75 or 80% of the total power, which is used generally during the hover. If I know the induced power, it is a very basic calculation from the textbook. Induced power is equal to the T into Vi. That means whatever the thrust, whatever the weight is required by for the helicopter, that into Vi. That means again it is coming T also I know that is Vi, I know that is equal to T by 2 rho A. So rho is the density. So for that altitude, I have to consider density and I have to consider the blade area. Find out the Vi, again multiply with the T. T is whatever all of it is there. So I calculate the Vi. If today somebody tells me that I will give you an engine which can deliver 700 or 600 kilowatt at 7 kilometer altitude, then I will find out what is the induced power. If I know the induced power, I can calculate that what will be blade area. Because everything comes in that all equations. It is like X kilowatt of power delivered by the engine at that particular altitude. What is the induced power? From the induced power, I will calculate what is the T into Vi. That means T is all everywhere in the picture. And what customer wants. Suppose customer wanted that at that altitude, I want to lift up some 4,000 kg or 5,000 kg or something, whatever all of it. Whatever. So I will keep that T. T is a function of the all of it. I will T that. That means it comes to T square. Then there it is a function of the radius of the blade. From there the rotor will be designed. Okay. For that means if somebody wanted that the helicopter to operate at a very higher altitude with this all of it, then what should be the diameter of the rotor? From that it derives. That is a basic fundamental. First, we also, when you do initial design, we start from this basic equation only. I think, is it clear, sir?
Thank you, sir. So then there is another question regarding if any flight simulations tools and softwares were used, or what software and tools were used to design this vehicle. I mean, for different aerodynamics part or maybe flight mechanics.
Speaking anyway, so these are all, we have some mathematical tools which has been given by during the design phase. So, and we have developed some in-house tools also to assess, because before going for a flight, pilot will ask the designer, I am going to fly at certain speed, but I am going to lift up certain weight. What is my control requirements? So we have some mathematical tools. It is like from the basics. We have some mathematical tools which have been developed in-house. So with respect to that, we calculate what is the control requirements and what is the we calculate even what is the loads going to be observed during the flight conditions, and what is the power requirement. All those things we mathematically calculate and tell a pilot this one before he goes for the flight. Otherwise, he won't go for the flight. He will ask generally, what will my control requirement if I'm flying at certain 200 kmph or 270 kmph or 250 kmph. So we have our in-house tools which has been used extensively to establish the performance and the handling quality of the helicopter before proceeding for any flight.
Yeah, that is really nice. Thank you. Any more questions from the audience?
Sir, I have one more question. So this is regarding the cold air and hot air trials. Sir, do you have any parameters that you consider for this hot air and cold air weather condition trials?
Which parameter means? Which parameter you mean? Just
in terms of performance. Sir.
Yeah. Okay. Now you see that when you think about the engine at the cold during the cold temperature condition, engine will develop the higher power. and the hot condition engine will develop the low power. Okay, so why I have to test? So when I take the helicopter to that conditions, definitely for a particular allopate, it will allow me to fly at a faster speed at cold weather conditions and at a lower speed at the hot weather conditions. When you give a performance chart for any helicopter, worldwide, if you see any helicopter, when you give a performance chart, you have to define this one, that if I'm operating at cold weather conditions, what speed I can fly, and if I'm operating at a higher hot conditions, what speed I can fly, or if I'm operating at a ambient normal conditions, like here you take Bangalore or you take your Kanpur in July or August or something, I don't know, in normal temperature conditions, what speed I can fly. So when I go to a cold weather, I assess the handling qualities, because you know this one, that even handling qualities also may deteriorate when you operate at a cold temperature conditions. That also I assess. Is there any observations are there? Then anyway, loads on the component will get reduced because you are operating at very low critical conditions. So particularly respect to handling quality I assess. And with respect to performance, anyway I will get a better performance. Generally cold weather when I go, I check that all the systems, what has been integrated in helicopter, how it is behavior. But finally it has to be subjected to cold and hot condition during the operational scenario. I think I could able to answer your question.
Yes, sir. Thank you, sir. And a nice presentation, sir.
Welcome. Thank you.
Hello, sir.
Yeah.
So just one more question. So as I was the same person asking about the fundamental design changes for an high altitude hovering.
Nice.
So sir, like I mean, so I have seen helicopters which are using twin blades, 2 blades, 3 blades, 4 blades, like
Yeah,
that.
yeah. Yes.
So
yes.
how do you decide on that? Like I mean, I meant like that in that way, like all the other aspects that doesn't take count of the fundamental lifting and all.
Yeah.
Like all the other aspects. Yeah.
See now, when you design, I have told you now, when you design a helicopter, first you have to see this one, that I have told you with respect to hover, when I design, I will give importance to the radius of the blade. Okay, as I have told you, see, for the blade loading consists of two parts. One part during hover, other part is during forward flight. When I consider during hover, I have to consider always the radius of the helicopter. That means my blade area will be pi r square only. When I consider the forward speed, I have to consider the blade loading with respect to the chord. That means there, the blade area won't be pi r square, it will be BCR. That means how many number of blades and what is the chord and what is the radius. So with respect to hover, the blade loading comes with as a function of pi r square. With respect to forward flight, it comes as a function of the VCR. There the blade area will convert into VCR. So when I do all these analysis, it is like a hit and trial method. I have to take a decision on that, because I have to satisfy the forward speed, I have to satisfy the hover conditions also. So when I select a radius, and I know that customer wanted that this helicopter to operate under these conditions, I will define one radius and then keep quiet this, and okay, for hover I am satisfied now. Now for this radius, whether can I comply the forward speed requirements of the helicopter? Then I started tweaking the radius of the chord of the blade. That means that is come the C. And then there comes the B. How many blades? If blades are 2 or 3 or 4. So then the number comes. So because once you see, always my aim should be there. If I will use a lesser blade loading, that means my blade loading will be lesser, then I can go at a faster speed also. So that is a function of blade loading. So blade loading means what? Whatever the total allopate I am going to fly, if it is a W divided by VCR. V means number. That means denominator, it is the number of blades. So the blade number is to go on increasing. That means you should not increase at a very higher number. That means I should not put some 5, 6, 7 or 8 blades. If I use specifically some 3 to 4 blades, at least my blade loading will be reduced, because that is a denominator. Once B increases, my blade loading also reduce, and when chord also increases, my blade loading will reduce. But if R increases, because once R increase, it will give me benefit with respect to forward flight also and with respect to hover also. Because once radius is increased, I will get a very good hover performance.
So thanks.
Is it okay?
Yeah, thanks a lot.
So there is one more question that has come. That is, how can this helicopter be upgraded to fit future weapons? I mean, like, has any provision been made to account for, I mean, additional weapons or some futuristic point of view? I mean, how upgradable is the helicopter? That is the question.
Now, presently, the helicopter is capable of getting integrated with rocket pods and then air-to-air missiles. In the future, anyway, it is generally what will happen. The weapons cannot be given by our helicopter OEM. That will be decided by the defense forces. So they will decide that presently, as on today, they have clearly told us we are going to get rocket parts and missiles. So in the future, if customer comes with certain requirements, because we have designed our wing to cater for almost 300 kg. Tomorrow customer comes with any other equipment, like any other external, so those can be integrated and done the test. Like suppose now DRDO is developing an Helena missile. So if tomorrow in the future, if Helena missile comes, we'll integrate it on the helicopter and then we'll demonstrate to the customer so that he can utilize for the future. We do not do any modifications on the helicopter because it has been designed. The helicopter designed for a specific all of it. And we have designed our armament wing also to cater for this external stores. So that can be carried. Only certain with certain specific testing, the system can be cleared.
Right. So that means, I mean, it is already provision, and
Yes, sir. Yes. Yeah.
so as long as it meets the within the weight requirement and other things, I mean, it is fine to, it is
Yes,
easy to.
yes, yes, sir. Yes, sir.
So I think, I
Sir.
mean,
I have one question.
Yeah.
So, sir, like there is a certain kind of restrictions as per the certification agency, like the helicopter shall not cross the limit of this, like some limit might be there in a decibel of sound, it won't cross. So what kind of testing you have done for to avail that, and how this like
See,
sound
now-
acoustics will affect the aerodynamics performance of the helicopter?
Now, if you'll go through the textbook also, if you go to the helicopter aerodynamics, I'll tell you one book also. It is helicopter aerodynamics by Prouty. One book is there. If you go to the last page in the preliminary design phase, they have given a diagram. That see, generally to avoid all these acoustics or vibration issues, we designed the tip speed of the helicopter. This is the tip speed of the helicopter. Like our helicopter also, we have designed for a tip speed around 220 meters per second. So the tip speed has been designed in such a way that to be away from the acoustic issues or vibration issues. So their tip speed comes into picture. So we have designed our tip speed, need to know, it is like omega into r. The radius, whatever radius you have designed for the helicopter, that should withstand that. Tip speed is equal to, it is like omega r. Whatever at what speed our helicopter blade rotates, 2 pi n by 16, that is called omega, into radius of the blade, that is called r. So generally for all these helicopters, if you see, to avoid all these acoustic issues, it has been designed from 210 to 220 or 25 meters per second tip speed, so that you should not enter into those zone. So we also designed even worldwide also, you see, every helicopter has been designed in such a way this one that at least not to go away from this range, so that you should not get into all these acoustics or vibration issues or noise issues, can tell indirectly.
so any more questions? So I just have one quick question regarding, I mean, has the production started for the LCH? I mean, are there any
Sir,
already?
it has a production already, this one, that in recent news also you would have seen, already production has started, and it has been already units have been established for Indian Army and Indian Air Force also. And
So when
they are
will
only
the-
the Honorable Defense Minister has renamed LCH
Right,
as
right.
present. So
Right,
it has
right.
been already, it is there in the Air Force also, it is there in the Army also, it is helicopters are there.
So
that
already
also-
some units have already been supplied to Army and
yeah,
Air
yeah,
Force?
already helicopters have gone already.
That is great. That
It
is
is there
great.
already, this one, that it is a proud for Indian defense community also.
No, it is a great pride for, I mean, the whole Indian aerospace community and all of us as Indians, that, I mean, this light combat helicopter has now, I mean, proven, and it is now inducted in the Indian Defense Forces. So thank you so much, sir, for all your time and being so patient to answer so many questions, I mean, from people. Okay. So thank you again.
Thank
Now
you,
we'll move to the next presenter. I will share my screen.
Thank you, sir.
Thank
Thanks
you,
a
sir.
lot.
Thank you. Thank you.
Thanks.
So next presentation is by Dr. Nidhish Raj. He received his PhD in aerospace engineering from IIT Kanpur in 2019. His area of expertise is in developing control, guidance, and estimation algorithms for aerospace applications. Currently, he is a senior researcher at Technology Innovation Institute in Abu Dhabi. Before that, he worked as a postdoctoral researcher at the German Aerospace Center DLR, where he focused on guidance, control, and system identification of HAPS, which is high altitude pseudo satellite systems. So with that, I'll request Dr. Nidhish Raj to share his screen and start giving his presentation.
Thank you for introducing me. For those of you who don't know, he's also my PhD advisor. So I have known him for since
I was. I'm no longer your PhD advisor. I was your advisor.
I was. I mean, he was. And yeah, thank you for the introduction. So let me just share the screen with you now. Can you see my screen now?
Yes, it is visible. Yes, you can make it full screen.
Yeah. Okay, maybe I have to stop presenting and then make it full screen. Just give me a second.
Sure. No, go ahead and take your time. I think what the screen you shared, I mean, it was showing the whole screen. So maybe once you go to the slideshow mode, it will show up.
Okay, got it. Can you see it now?
Yes.
Okay. So I have agreed to talk on this topic of unified control for Tailsitter VTOL. So I couldn't put too many slides for this talk. So please feel free to ask questions if you have any. So here are some Tailsitter aircrafts. So Tailsitter aircrafts, from the name as it suggests, they take off and land on their tail. And here are a few examples of them. So first you have this Convoyer Pogo, one of the first Tailsitter aircrafts. So this has made its first flight in 1954. It had taken off and did the back transition and landing. And then you have another one from Aerodynamics, 2006. And then you have this humble biplane quadrotor, which was part of my thesis. It was developed way back in 2016 in IIT Kanpur Aerospace Department. So how do they work? So it's not very difficult to understand. So they have this main rotor or thrust, or multiple rotors in this case. They develop the thrust, and so most of these tailsitters, they have control surfaces on the tail and on the wing, which is used for controlling the attitude. The roll, pitch, and yaw are usually taken care of by the control surfaces on the tail as well as. And here also it is the same configuration. So you have similar control structure. But in this case, you have a quadrotor. So the roll, pitch, and yaw is being controlled by regular quadrotor mode control during takeoff and landing. And so during the forward transition, the entire aircraft tilts by 90 degrees, it pitches down, and then it operates as a fixed wing aircraft. And then after its mission, it tries to do the back transition, wherein it pitches back into the hovering configuration, and then it lands on its tail. So that is how it works. And you can see like how long it has been there. So from one of the first tailsitters way back in 1954 to, till today, people are still developing tailsitters because of several advantages they have got. One of them being mechanical simplicity when compared to other VTOL aircrafts. So let's look at the other configurations for VTOL. Here is a very simple, probably the simplest VTOL that you can find is the quad plane, wherein you have a quadrotor or multi-rotor configuration attached to an aircraft like this, airplane configuration. And this kind of configuration is very popular because they are very simple mechanically, and also from the controls point of view, it's very straightforward. You have independent functions. Like when you're hovering, you just need to operate the multi-rotor mode, and it's very well known. And it's also very easy to build. And when you are in fixed wing mode, you just need to operate the fixed wing propeller, and then you can use the control surfaces to control the aircraft. And also, like, it's pretty straightforward by all means, and this is why this is very popular. And but the only problem with this kind of configuration is that you always have to carry these extra motors and propellers, which is always useless for most of the mission, because you take off and land, that's when you use these. And for most of the mission, which is, I would say 95% of the time, you are not using these motors. So that is one big disadvantage with this kind of configuration, which is why people prefer other configurations like tailsitter or tilt rotor or tilt wing. So tilt rotor is more complicated mechanically. You have these huge rotors which are rotating. So this is one of these examples of a tilt rotor. And here the roll and pitch control is accomplished through cyclic and also collective, differential collective of these rotors. And so here only the rotor rotates from this vertical position to horizontal orientation, and then the aircraft is in normal cruise mode. So in case of tilt wing, you have all these rotors, and then the entire wing is aligned with the rotor, and the whole thing rotates instead of just the rotors in case of tilt rotor, and the fuselage always remains horizontal. So this is mechanically more complicated than just tilt rotor, because you also have to tilt the wings. But hover performance wise, I think this should be slightly better, because this wing is aligned with the flow. And yeah, but then this is control wise, the tilt rotor and tilt wing are less complicated than tailsitters, because there the entire airframe is rotating. So another interesting thing about these systems is that as you go from quad plane to tilt wing, the interaction of the hover flow with the airframe increases, and you need greater modeling effort to understand how the flow interacts with the wing. For example, here, the flow of these rotors, they interact with these wings. Here, the interaction is even more. So there is more modeling effort and understanding required to operate this kind of vehicles. And it's even more complicated for tailsitters. So we know that like tailsitters have got these two. In fact, all VTOL aircrafts, convertible aircrafts, have got these two modes: fixed wing mode, and then you have the rotary wing mode. Fixed wing mode, it does normal cruise and flies like a fixed wing aircraft. It's much more efficient in this mode for traveling longer distances, and even for a given payload, this will consume. This is supposed to consume less power. And then you have rotary wing mode, which is used for takeoff and landing. And this is the configuration. And these individual modes, they have different methods of controls, and they are very different. So you cannot have, just one controller wherein you can control the entire aircraft. So you need to have these two conventional controllers whenever you design a tailsitter or a tilt rotor or a tilt wing or even a quad plane, because and in quad plane it's much simpler because they are completely independent and completely decoupled, unless you are in the transition regime wherein you go from hovering mode to fixed wing mode and vice versa. So from the point of view of guidance, they are different. So fixed wing and rotary wing modes are different in the sense that aircrafts can only do path following. They cannot do trajectory tracking. So trajectory is a path, is a time parameterized path. So there is also a time parameter associated with a path. And a path is just a XYZ coordinate. So most rotary wing aircrafts, especially the smaller ones like these quad rotors and all, they can do very well trajectory tracking because they can slow down as much as they wish, and they can also go backwards. So that means this time parameterization can be strictly followed if it is within the limits of the rotorcraft. So that is one main difference. And in terms of position control, the fixed wing accomplishes the path following by changing the course, which in turn is accomplished by changing the bank angle. Whereas in case of rotary wing, you can change the orientation of the thrust vector to move in any direction. So that is how you accomplish position control. And here the aim in case of fixed wing is to follow a path very tightly. Whereas in case of rotary wing, you can follow a time parameterized path, and also you can make it hover exactly at any location you wish. So here, in case of fixed wing, the airspeed is, let's say you are considering a decoupled system. The airspeed is typically controlled by thrust, and altitude is typically controlled by pitch angle changes. Yeah. Whereas in case of rotary wing aircraft, the airspeed is controlled by pitch angle changes, and altitude is controlled by thrust, changing the total thrust. But in fixed wing, larger fixed wings, and also if you consider like more advanced control techniques, then the airspeed and altitude are very much coupled, and they use what is known as TEX control, total energy control system, wherein they consider both of them together. But either ways, the control approach for these two parameters are very different for fixed wing and rotary wing. And that is the reason why you cannot have like one single controller for both these modes. So also in case of fixed wing, the attitude control is accomplished through the control surfaces. So you have the elevator for pitch, ailerons for the roll, and rudders for yaw control. And for helicopters, the attitude control is accomplished through cyclic control input. And for multi-rotors, you have variable speed motors, or even variable pitch motors, which you can use to apply control moments. So again, these are very different control techniques, which is used for controlling. But somehow for fixed wing, tailsitters, at the level of the attitude, you can have some kind of unification, wherein you can have just one controller. So the idea of this talk is to explain how you can use a single controller and simplify a lot of things when it comes to tailsitter control. So here are some of the problems that you will face with tailsitters. So here is a tailsitter biplane. So it's just a quadrotor with two wings attached to it like this. And so in quadrotor mode, so the rotors are supporting the weight. And in fixed wing mode, the two wings are generating lift to support the weight. So there are three key differences, three key difficulties associated with controlling the vehicle. One is, how would you command the vehicle? For example, if you want to give roll command in the quadrotor mode, you would expect the vehicle to rotate about this body frame EX axis. Likewise, if you want to give the same roll command in the fixed wing mode, you want the vehicle to rotate about the body frame EZ axis. And what happens in between as you transition from quadrotor mode to biplane mode or fixed wing mode, as the tilt angle, the pitch angle changes, how would you expect the roll to change? So that is one problem, like how do you give command to the vehicle? Let's say you are trying to fly it manually. And the second difficulty is with regard to control allocation. So here, let's say you want to do roll about EX axis. In that case, these two motors or these two rotors are going to increase the thrust, and these two are going to decrease the thrust, and then you get a positive rolling moment about EX axis. Yeah. So the way you accomplish the control is also different. Likewise, here, if you want to generate a roll, then you need to do something else. For example, you need to actuate the ailerons. So ailerons are not visible in these pictures, but they are there. So for the same desired movement of the aircraft, you have to use different actuators. So there is a problem. So another issue is with regard to stable transition. So can you accomplish steady state transitions. That means, let's say your aircraft is initially like this, and at some point it is at 45-degree pitch angle, yeah, minus 45-degree pitch angle. In that case, is it possible for you to maintain that pitch in a stable sense? So, or let's say at any other intermediate attitude, is it possible to maintain it, maintain stability? Why is this important? This may not be very important for small scale tail sitters, but for large scale tail sitters, you may want to stop your transition because the transition is going to take much longer, and you may want to stop it and bring it back. So it is important to also think about stability during the transition, because the common autopilot open source codes that you see these days, the transition is an open loop phenomena wherein you just have some time, and the idea is to pitch the aircraft from multi-rotor mode to the fixed wing mode, let's say in few seconds, maybe 5 or 6 seconds. Yeah. So there it's not going to be a big problem, but usually it is going to be a problem when you consider larger tail sitters. So these are the 3 issues that you face when you are dealing with tail sitters. So let's see if we can simplify these issues and try to see if there is an elegant solution to solve all these issues together. So that is why I made the title of this talk as Unified Control for Tail Sitter. So do we need separate controllers for each mode? Yes, we need separate controllers, but only up to a point. Like we only need separate controllers up to position control. For attitude control, you can have a simplified unified controller, which is going to solve all the 3 the issues that was mentioned in the previous slide. So how does a simple control framework look like? For example, in the open source autopilots that you find, you will find that they have like 2 different modes, and then they somehow try to switch the modes from multi-rotor to fixed wing under certain conditions, and they have a state machines for switching this mode. And this happens only after the attitude controller. It doesn't happen before the attitude controller. And this particular method has several issues. For example, if you are switching from multi-rotor to fixed wing mode after a certain speed, this could lead to actuator discontinuities, which can also, sometimes excite some of the frequencies of the aircraft, if you're considering larger tail sitters and all. So this can be a problem. And also this doesn't seem to be a very elegant solution, because a lot of code needs to be written in order to accomplish the switch from one mode to another mode. If you go through the code, you will understand like it's fairly complicated, and all this because you are using a very simplified approach, simple switch kind of mechanism to accomplish the transition or to control the entire tail sitter during the 2 modes of operation. So what does this unified control framework look like? So here you have like the fixed wing control framework and also the rotary wing control framework. And also in between you have the transition control framework, wherein you can have a stable transition. So for the fixed wing, again, here, you can use your regular L1 guidance, and for multi-rotor, you can use your regular PID. And for transition guidance, you can use whatever you wish. Maybe PID would be better. And for position, you can do path following when it is in fixed wing mode, and trajectory tracking, or even path following in case of rotary wing flight. And in case of transition, you can have your own, specific transition, specific forward transition or backward transition, specific position controller in place. And then you also have here a state machine, which can be used to switch from one to another. And this, if you implement this particular code, this entire code is going to be much more simpler and decoupled, because in the previous approach, if you have to do it, everything is coupled together. For example, if you have a fixed wing code which is only meant for fixed wing, and a rotary wing code which is only meant for rotary wing, And if you need to accomplish this kind of switching, you need to have separate conditions in each of these different levels to accomplish the switching. So that means you need to modify the individual fixed wing and rotary wing codes in order to accomplish this. But if you take this approach, you don't need to touch any of these code. Like you can have it as it is for fixed wing, the guidance and the position controller. And likewise, you don't have to touch any of the rotary wing code. Only thing is that you just need to have a simple transition guidance and transition position controller in place. And then you need to have a unified attitude controller plus controller allocation, which is something which you need to write. But this is something very simple. I'll explain in a couple of slides like how you can simplify it. And this approach deals with all the three problems that I mentioned earlier. And here and this controller is going to command the actuators. And because you have a unified controller for all the three modes, you will not find any actuator discontinuities. So how do you accomplish this unified control method? So there are two key steps in order to accomplish that. First is with regard to attitude command. So how do you give command to a tailsitter so that you can use the same command in both tailsitter mode as well as fixed wing mode? So for that, you need a 3-1-2 Euler sequence as an attitude command instead of 3-2-1, because in aerospace applications, especially in airplane and fixed wing applications, we use 3-1 Euler sequence all the time. Or let's say you are not doing large angle maneuvers, then you can use 3-1 Euler sequence, Euler angles for control of attitude. You can also use it for specifying the attitude and also use it for feedback purposes. So your entire controller can be given in terms of 3-1 Euler angle sequence. But because we are dealing with tailsitter, we cannot use 3-1 sequence because in 3-1 sequence, you have singularity at pitch angle of plus or minus 90 degrees here. But this plus or minus 90 degree is within the operational range of a tailsitter. So obviously we cannot use 3-1 sequence, but there are so many other different sequences that we could use. But 3-1-2 sequence is ideally suited for tailsitter for many reasons, because one of the reason being that in 3-1-2 sequence, when you do a roll command, the entire aircraft rotates about the horizontal velocity vector. Let's say you are doing a stable transition wherein you are not, you are maintaining a steady height and you are doing the transition, then the velocity vector is horizontal, yeah. And then when you do a roll at any intermediate transition point, you are basically rotating the entire aircraft about the velocity vector. That means you are, during the roll process, you are trying to maintain the same angle of attack, which is very important because you don't want to change your angle of attack while you are rolling. Let's say if you use 3-2-1 sequence, in that case, if you try to do, let's say you are somewhere at 45 degree of pitch angle, and then you try to do the roll, then the aircraft rotates about the body frame x-axis. That means you are converting your angle of attack into angle of side slip, and you will lose a lot of lift. So that is a big issue with 3-2-1 sequence. So, but with 3-1-2 sequence, as you are rotating about the velocity vector, you will not feel aerodynamically a big change. And another issue, advantage is it gives you uniform controllability throughout the transition, as I mentioned. And again, there is no singularity at plus or minus 90 degree of roll. So you can use 3-1-2 sequence to specify the angle, not to do the feedback control, because to do the feedback control, it's better to use the geometric control, wherein you use directly the rotation matrix to do the feedback control. So in a couple of slides, I can show you how it is done. The advantage with this, the advantage with using rotation matrix is that it is globally valid. That means for any orientation, the rotation matrix is unique and well-defined. And also, if you use rotation matrix for feedback control, we can also show mathematically that it is almost globally stable. So in other words, like it's globally stable. And it is very easy to implement. So this is what I was mentioning earlier about what does roll mean when you use 3-1-2 sequence, Euler sequence. So here is your initial body frame. So here is the x-axis, y-axis, z-axis. And then let's say you pitch by, let's say some angle, say 30 degrees or something. So this is your new pitch, which is like this red line. And if you try to roll the aircraft, now you can see that this angle is maintained. So it is more like a cone. The trajectory of the x-axis of the body frame x-axis is like a cone. So if this is your horizontal x-axis, initial x-axis, and if you are doing the transition along this line like this in this direction, the velocity vector will be in this direction, and you can see that as the aircraft is rolled, the angle of attack is maintained because this cone angle is maintained. So this is the preferred, I would say, the preferred way to command the attitude while the aircraft, the tail sitter is transitioning. So and how do you do attitude control using rotation matrices? So you need to define a new, let's say that R is the current orientation and omega is the body frame angular velocity. And similarly, RD is the desired attitude and omega D is the desired angular velocity. And this RD is basically coming from the 3-1-2 Euler sequence, which you define as a pilot, which you define that can be converted into an equivalent rotation matrix. And then you have this, and omega D can also be similarly defined from the command. And once you get R omega, RD omega D, you don't need any more information to do the feedback control. So you need to define an error rotation matrix, which is RD transpose R, and then an error angular velocity, which is this omega minus RE transpose omega T. And with these two, just using RE, you can define a rotation error vector ER, which is this. And here P can be just an identity matrix. It's just, you can also keep it as any positive definite matrix with different eigenvalues. And if you choose all these, with all these things defined, it's possible to define the control moment which should be acting on the tail sitter in the body frame, like so. And you can see this is entirely made of the above mentioned terms, ER, E omega, omega, R, RD, and omega D. And also there is J, which is the moment of inertia of the tail sitter. So with this, if you apply this control moment on the aircraft, all these properties are achieved. And you also have a unified control approach like this, like a single attitude controller can be used, and all the other issues that I have mentioned, it's mitigated. So what are the advantages of unified control method? One advantage, big advantage, is that you can use CFD and wind tunnel data to model the forces and moments acting on the tail sitter as it is transitioning. So you have very good idea of what is the moment and force acting on the tail sitter at each angle of transition. And then correspondingly, with that knowledge, you can design your feedback controller so that you can ensure that the tail sitter is stable throughout the transition maneuver. And stability is guaranteed because you have used this controller, which has got very nice stability properties, like it's globally stable, almost globally stable. And it's a very elegant approach because if you are flying this aircraft, you can give simple, it's possible to specify the attitude as a manual flyer even during the transition, and you can actually fly it at various pitch angles. I'll just show you the video in the next slide. And the software is very simple because let's say you are implementing this unified control approach. Basically, you need like 4 lines of code to implement it, and it's not very complicated. Like you can implement something like this even on very tiny microcontrollers with not so much of computational power. And another advantage is that, again, as I mentioned, the actuator control is continuous. There is no discontinuity anywhere, because you have like one single attitude control for throughout the flight maneuver. So the next slide, I'm going to show you the video. So this was done in the IIT Kanpur airstrip, and this flight was done manually. So you can see like how easy it is to fly Tailsitter manually without any extra support, just using this technique of unified control.
So this, I mean, when you are saying that, I mean, you can fly it at any altitude, sort of, that means that, I mean, there are practically many trim points possible.
Sorry, I couldn't hear you.
Yeah, so what I was saying is that, I mean, the point where you say that you can actually, because having a unified control, you can fly it at any altitude.
Okay.
I mean, does it imply that the vehicle will have actually many trim positions? That is, I mean, I can fly it, I mean, of course, at 90 degrees as a quad rotor, and I can fly it practically at any intermediate point between 90 degrees and 0 degrees?
Yeah, it is possible.
Okay.
Yeah, I have verified it with the biplane.
Okay.
I just realized that I don't have much of a control on the video. So that was my last slide.
Yeah. So right. So that gives us some time for question and answers.
Yeah.
Do we have, if you have a question, Sami, of your own, I mean, you can ask by unmuting or you can type it in the chat box.
Hello. I'm audible.
Yes, please go ahead. Yeah.
So I have a couple of questions. Like, if for the tilt wing, like in V22 Ospero and all, we ideally are seeing while the transition from while during the transition, there will be a slightly drop in altitude. So is any kind of issue you has arrived with during the transition from rotary wing to biplane mode?
Yeah. So when you do the transition, forward transition, usually there is not much change. So yeah, sometimes the altitude drops and sometimes it goes up. It depends on the wind actually. So for that, you will need some kind of feedback control plus feed forward control to fix that issue. So we had done some work on that while I was at IIT Kanpur. So there was a learning-based, iterative learning-based controller which was implemented. After which we were able to accomplish forward transition with less than 50 centimeter change in altitude. So yeah, you need to have some kind of control to avoid this kind of change in altitude. And you can also, you will see the largest change in altitude during back transition. What happens is that when you do the back transition, it goes up high a lot. Like the change in altitude is much larger when compared to forward transition. So there also you could do some kind of feedback control plus feed forward control or learning based control to have a better transition.
And which airfoil like you have used for the wing? Any special series? Yeah, for symmetric camber like.
So here we have used a symmetric one. It's I think NACA 0015 or something. Yeah.
But it is possible to use other airfoils also. I mean, as long as the pitching moment is not very high.
Yeah, sure.
Because of the symmetric airfoil, you have a like a certain alpha during the forward flight.
Yes. Yes.
And you are using the electric motors, right?
Yeah.
So I have seen from the peak like there is a slightly inward tilt in all the four motors. Inward tilt is given.
Yeah.
So what's the reason for that?
So that was done to increase the control authority in yaw. So if you tilt it like that, you will have a greater yawing moment when you change the differential speed of the diametrically opposite motors. So otherwise, you will not have enough yaw control authority because this is not just a simple quad rotor. You have these large wings, and that means you have a lot of damping in the body frame Z axis. So to overcome that, you have we put these motors at slightly tilted angle.
Okay, and like I can see from that video only like you are using that Pixoc 2.4.8. So flight controller.
2.4.8.
Yeah. Pixoc flight controller 2.4.8 or something.
Okay.
Right. So have you done any kind of changes in that to modify it for your Tailsitter?
Yeah, I think So you need to change the code for sure. Otherwise, whatever I mentioned, all those things have been implemented, and also a few other things you need to change to make it work for Tailsitter. So hardware wise, I haven't changed much. So the GPS in this particular vehicle, it actually tilts with the vehicle so that it is always pointing upward. But other than that, there is no hardware changes from the Pixox side.
I mean, I believe his question probably is related to whether you are, I mean, using some stock software from Pixoc, or you written your own. I mean, made your own.
Yes.
So yeah, the code only that part of the code which corresponds to biplane has been changed, because the estimator and all we don't need to change, because it works very well for all the aircrafts, like either for fixed wing or multi-rotor, it's more or less the same. And even for tail sitters, you can use the same estimator. But for controller, yes, you need to change the controller. So I have written the controller for the tail sitter separately. I think there is one question in chat. Which part is more challenging to control, transitioning during takeoff or landing? I would say both of them are equally challenging, but I think for landing it is a bit more tricky, because the change in altitude that you observe during back transition is much more than the change that you observe during forward transition. But for larger aircraft, I think both of them are equally challenging.
Right. And I mean, also that because that is inevitable in some sense, because you are flying at high speed and then you are now arresting that speed very quickly.
Yeah.
So that actually ends up resulting in some gain of height.
Yeah, that's right. Yeah.
So any more questions from the audience?
Yes, sir. So, as you said, like when it's in the quadrotor mode, the GPS is horizontal. Oh, sorry, vertical. It's pointing in the upward direction, and so if you want to do trajectory tracking in case of a quadrotor mode, say if you want to do a position hold, so in that case also it uses GPS coordinates, right?
Yeah.
But the GPS itself is like it's the frame of the GPS itself is rotated. So
Yeah.
how do you take care of that thing?
GPS as such, it doesn't have any orientation. So GPS is going to give you the estimate of the location. Yeah. So location does not have any orientation. So you can keep it in any orientation. The reason for keeping the GPS horizontal is that you need to see as many satellites as you can, and keeping it in the horizontal position will give you visibility for as many satellites for a given location. So you can keep GPS in any orientation, but the location is the same, right? Because GPS gives you the location.
And actually, Tanay, to add to what Dr. Nidhish actually said, later experiments, later vehicles and other systems that we have built, we started keeping the GPS in the vertical orientation all the time. So in that sense, the GPS is actually in the fixed position. It is put on the wing and in the vertical orientation. And because what happens, after transition anyway, most of the time you are flying like an airplane, so then it becomes horizontal. So as such, actually, we never experienced any problem, whether in horizontal or vertical orientation with the GPS receiver so much. So it was initially taken as done as a precaution, and later on through experiment, we realized that it doesn't make much difference, whichever way you put it actually.
Mm-hmm. Yeah, another thing is that if you are using GPS-based compass, then it is going to be a problem. So we don't use that compass for. So at least in this video, I disconnected the GPS compass. So it's okay. The assumption in Pixoc and other open source autopilot is that the GPS is attached fixed relative to the aircraft frame, so that whenever you see, this cannot be done if you have like a tilting based GPS, then you need to change the firmware for that. So we disconnected the compass, the magnetometer, and then with just the GPS connected, it shouldn't be a problem.
Any more questions from the audience?
Hello. Yeah, as you pointed out, GPS location doesn't matter even if we are placing in vertical frame or horizontal frame. So similar goes with the flight controller, or like there is a only fixed location, like fixed along the horizontal or along the vertical, we have to place the flight controller.
So the flight controller theoretically can be fixed in any orientation, but you always try to orient it in such a way that the principal axis of the flight controller, the XYZ, is aligned with the body frame axis. So you can choose either one, right? Like any of them. Like for example, X can be aligned with Z, but all the principal axes should be aligned with each other, whichever order you choose. So that can be configured in the flight controller firmware usually. But theoretically, you can orient it in whichever way you choose. But the thing is, like once you attach the flight controller onto the airframe, then you cannot change it while it is flying, because then you are going to be in a lot of trouble.
Any other questions from audience? If there are no further questions, then let's thank Dr. Nidhish Raj for this very nice presentation and very detailed discussion on the way he developed the autopilot or other attitude controller for the biplane tailsitter vehicle. He actually has built various kinds of that. I mean, he showed video of one of them, but other was actually the swiveling biplane tailsitter, which was even more interesting than the current vehicle. I was hoping he would talk about that also a little bit, but that is fine. Yeah, so
I wanted to, but then you said I shouldn't make the talk very mathematical. So I didn't put it. I was going to.
Okay.
Yeah.
Yes, that is true. Yes. So yeah, I mean, that was a constraint. I didn't want it to, get too academic, I would say. Okay? I mean, keep it more interesting and more from the perspective of difference. So, all right. So thank you so much for sparing time and coming to present here to all the students and other participants from outside of IIT. So
thank you very much for the opportunity.
And for the rest of the people, I mean, we'll now take a break and we'll resume back at 6:30. So we have two very interesting talks now. One talk is actually on development of fuel cells for aerial vehicles. So how fuel cells can actually be a game changer in the coming days to increase the endurance. So right now, I mean, typically for aerial vehicles, we have two options, especially small unmanned aerial vehicles. We have option of either using a battery powered device or a normal gasoline based device. Gasoline based device, I mean, tend to be slightly dirty, complicated, and noisy. But electrical devices are preferred, but then they suffer from the problem of low endurance. So that's where, I mean, the fuel cell could be really game changer. And then we will have last presentation, which is also a very nice topic. I mean, by my friend and colleague, Dr. Jayant Sirohi from University of Texas at Austin. So he will be talking about a payload delivery system using auto rotation method. Okay, so it is a very nice talk again that will start from 7:30. So I'll hope to see you all. I'll keep the link open. So the same link will be used, and we'll just set off for another half an hour or so, and we'll join back again later. Okay, so thank you very much for joining, and I hope to see you all again at 6:30.